Good morning, Calculus. I totally forgot to post this video, and it's because I forgot to make this video. But here we are now, talk you through integration and antiderivatives, which to us is basically the same thing. We'll talk about the nitpicky difference later, but for right now, those are interchangeable. So this assignment is all about undoing derivatives, right? We have these last unit's derivatives rules, and now we're working to do them backwards. I'm going to do a few examples, talk you through them, and then you'll do 12 examples for the assignment. As always, if you need help, message me on Teams, message your friends, watch my YouTube videos, watch other people's YouTube videos, ask in class, ask during office hours, a lot of options. Just don't, feel sad in your room wishing you could do calculus. We can make it happen. All right. Let's do it. Okay, so when we're doing the power rule, I'm going to look at last unit's derivative rules just as a refresh. Last unit, when we took the derivative of something that looked like a number times x to the power of n, we multiplied the two exponents and then knocked it down by 1, right? So if we were saying that we had some function and then its derivative was 24x to the 5th, that means 24 is these two numbers multiplied, and 5 is the exponent knocked down by 1. Okay, if 5 was the exponent knocked down by 1, the original exponent must have been 6. And then if 24 was 6 times something, the original coefficient must have been 4. So over here, we're going to write that this is 4 times x to the power of 6. And then we're going to put a plus c on the back. And I'll explain that at the very end of the video. But basically, anytime there's not numbers right here and right here, we're going to put a plus c. All right, so same thing here. We know that the exponent was kicked down by 1 when we took the derivative. So when we integrate it, it's going to be kicked up by 1. And then we're going to say 17 was 4 times some number, and that number goes here. And that number is going to be, we want the 4 to be gone, and we want there to be a 17. So it must have been 17 divided by 4. Kind of wacky, not a very cute number, but the right answer nonetheless. And then we're not going to forget to put the plus c on the back. Two of our other derivative rules were that if you take the derivative of numbers, just a regular number, you get 0. And if you take the derivative of like 3 times x, you would get 3. 10 times x, you'd get 10. Any m times x, you just get that m. So here, when the answer looks like just a number, the integral must have been 4x, that number times x. And then put our plus c, and the plus c comes from this rule. It comes from the fact that when we're checking our work, when we're saying, okay, if we took the derivative of our answer, would it give us what we were integrating? And you can always have a plus c in the back because the derivative is 0. And then that brings us to our final rule. How do we generalize this? How do we make it so that we can do this anytime? Okay, so we have a number times x to the power of another number. We know that the exponent is going to be kicked up by 1. And then just like in 17 over 4, we would take what we're trying to get and divide out what we know we're about to have to multiply by the exponent. And then we're going to put a plus c in the back. So that's our generalized power rule. Great. Let's move on to exponentials. We have some rules from last time. When we take the derivative of a to the power of x, so 5 to the power of x, 10 to the power of x, whatever, the derivative, when we take this derivative, it's equal to the natural log of that number times the function again, right, times that a to the power of x. So now we're saying if we have this in an integral, our integral is just going to be the a to the x. So here a is clearly 4, so our integral is 4 to the power of x plus c. Okay, we can mess with the coefficients a little bit, right? We can say whenever we had 5 to the power of x in the answer, there usually is this natural log of 5 constant. We don't have one here, so that's kind of odd. Basically, we do this. If we, wow, I said G instead of F. Bad. Here, if we had 5 to the power of x, let's do it like this instead. May not be confusing. We had 5 to the power of x. Our derivative would be the natural log of 5 times 5 to the power of x. Totally fine. If we had 3 times 5 to the power of x, then our derivative is 3 times the natural log of 5 times 5 to the power of x. So far, so good. If we then added in a 1 divided by the natural log of 5, then this also would be 1 divided by the natural log of 5 in the derivative, right? Because it's just a coefficient. This bottom thing can simplify to just 3 to the power of, or times 5 to the power of x, which is what we wanted, right? I am going to move things around so we can keep all these notes. Didn't quite work out like I wanted. That's fine. Good. Nope. Great. Boom. And this gives us that when we want the answer to our derivative problem to be 3 to the, times 5 to the power of x, that means our original function, or the integral, should have been 3 times 1 over the natural log of 5 times 5 to the power of x. And let's generalize this. Let's kick back to blue. When we have a to the power of x, it turns out that our integral, oh shoot, plus c. Our integral is going to be 1 divided by the natural log of a times a to the power of x plus c. This is something that you can think through every time if you really want to, but we're going to start a note sheet pretty soon. That's going to go straight on my note sheet. And I'm going to stop thinking pretty soon when I'm doing these problems. Same with this. This one's going to go straight on our note sheet, right, to be a reference. All right, last one. Do some trig stuff, and I'm going to move my face. What up? What's the last color I used? Nice. Okay. For trig, honestly, we look at our last unit's rules and we just do it backwards. And then anytime, so here we look at our last unit's rules, we do it backwards. We're looking for secant tangent. Secant tangent's right here. Must have been secant. Bada bing, plus c. Good to go. And now we look at something where we say, okay, let's find negative secant tangent on the list. Wait, negative secant tangent isn't on our list. All we have is this regular secant tangent, right? If our last unit's rules say it's positive, but our problem says it's negative, we just do the negative of whatever it would have been. So this is negative c plus c. So let me say that again. Here we've got negative cosine. Here we've got positive cosine. So we'll do the negative version of whatever was going on here. All right, y'all, that's integration, that's anti-differentiation. Right now, we're still working on just knowing how to integrate regular functions. And then we're going to start learning how to combine them in different patterns. And it's going to be great. So, yeah, you're going to do the worksheet. I'm going to scroll down. You can pause the video now. You can stop. You can work. I'm going to explain this plus C thing one more time, just so we have it on record. Okay. Plus C thing. All right, I should have made these notes beforehand. Basically, what this is doing is I'm going to talk about kind of how we did the assignment the other day in class. Oops. Paste. one of the better parts of online school. I can just copy paste things instead of writing them 1,000 times. Ooh, should have done it. Okay, so what if we have that the derivative of some mystery function, right, is, oh, I just don't know, 100x cubed, right? I say, what is the antiderivative? How do you do the derivative backwards here? How do you find a function whose derivative is 100x cubed? And I'm going to go ahead and paste that, and paste that, and paste that, because we're going to have a bunch of different answers. The first answer we're going to come up with is 25 times x to the fourth. Seems pretty good to me, right? When we take the derivative to check our work, we do 25 times 4, get 100. We do 4 minus 1, get 3. We're good to go. Amazing, right? But what if I had said 25 times x to the fourth plus 13? Right? When we take this derivative to check our work, so we take the derivative, we say 25 times x to the fourth, taking the derivative gives you 100x cubed, nice. And then when we take the derivative of 13, we get plus 0. That's fine, right? Adding 0 to something doesn't really matter, doesn't really change it. It's an additive identity. So we're fine, right? This is also a perfect answer. What if I had something like 25x to the fourth plus any number ever, right? That would still give us plus 0 and still would be a correct answer. So the way we're going to write this, the way we're going to write every single answer, quote unquote, every single answer, is just put a plus c, where c is a constant, aka any number. Right, and this is why, check, this box right here is why we put, shoot, nice. This is why we put plus c at the back of every integral, right? Because all of them were, it's a valid answer, and it represents all valid answers. All right, y'all, that's that for that. Again, reach out to ask for help. You can come to my office hours to talk math. You can talk about Garfield. You can talk about life. You don't really have to have a reason to drop by. You can come with your friends. You can come alone. You can ask me questions over messages. A lot of options. I'll see you in class.